The simplest way to get multithreading in Scala is using the parallel collections. So these are collections, much like the ones that we are used to, array and list and such, except these happen to process the contents in parallel in the various functions that they have. So they have the same types of methods that we're used to from array and list, but they do things in parallel. And these are in the Scala collection parallel package. And there are two subtypes to this: Scala collection parallel immutable and Scala collection parallel mutable. Much like you're used to with the standard collections, these have shorter lists of contents though. So for example, on the immutable, there's a par hash map, a hash set, iterable map range, sequence set, and vector. What you will notice is not here is a par list. And this is because the list, due to the way that it's stored, cannot really be processed well in parallel. So if you have a list and you try to do something in parallel with it, you get back a different type. Similarly, on the mutable side, there is a par array, and then many of the other types that were part of the mutable library are here. So how do you get one of these parallel collections? And once you have it, what can you do with it? Well, in order to understand that, let's go ahead and let's make a new application. And we will call this parallel collect. And I want to do something very simple here. So we're going to make a for loop that runs in parallel, just to show you how it's done. Now, a normal for loop, we might have done something like this. Now, it turns out this loop would not be interesting in parallel because it runs so remarkably fast. Okay? There's not much work going on here, and in order to really demonstrate things are happening in parallel, you need to slow stuff down a bit. So what I'm going to do, first off, is I am going to write an inefficient recursive Fibonacci function. So if n is less than 2, we'll give back 1, else we will give back fib of n minus 1 plus fib of n minus 2. The fact that the recursive Fibonacci is slow is actually exactly what I want here. And to help illustrate this purpose, we will count backwards from 30 to 15. So we're going to start with something that takes a long time to calculate and then go down to something that runs faster. When we run this, nothing is happening. Oh. By minus 1. That's an easy bug. Okay, so ranges don't count backwards by default. Okay, so here we go. Big numbers down to smaller numbers. This happens sequentially. Everything happened in order. If I want a parallel collection, I can make myself a par range simply by calling par on a range. The par method gives us back the parallel equivalent of it. And notice what happens here. The numbers do not come out in order from largest to smallest. They come out in what looks like reasonably random order. That is because the parallel collection takes each of these different numbers and potentially assigns it to different threads. So threads that get a smaller number tend to finish faster, print their value faster, and then they can go on and do the next number. So we get these things coming out in a different order, which is kind of our proof that this was happening in parallel. Okay, so technically if we had timed this, theoretically this sped up somewhat. Another thing that we should illustrate here, and we won't try to time this because I'm not really trying to get a speed up on this. We will look at some examples shortly where we're actually going to take this and get faster execution from it, but this is kind of a toy example here. Why don't we use parallel all the time? Why didn't we start off thinking about things in parallel? And the reason for this is because there are challenges with parallel. To understand that, we'll show you one of the fundamental problems with parallelism. This is something called a race condition. So I'm going to make a var called I, and I'm going to do something kind of dumb. I'm just going to have a loop that goes from 1 to 1,000,000, and inside of this loop I'm going to add 1 to I, and we're going to print line I. Now of course it should be pretty obvious what this does. At the end, I should be 1,000,000. Hey look, I is 1,000,000. Great. If I make this parallel, the result should not be changed. It should do the same thing, just perhaps happening faster, but it turns out it doesn't. Okay? You'll note that the last thing that was printed here is only 288,000. Not only was that not 1,000,000, that wasn't even very close to 1,000,000. Since I happen to be doing this on a machine that has potentially lots of threads, yeah, we can get some very small numbers out of here. What's going on? Why are these values not 1,000,000? To understand that, we kind of have to understand what's going on with the threads and the fact that this right here, while it's a very nice small line, actually is not as simple as it looks. When we do this, what's actually happening here is first we need to load the I value from memory. And once we have it loaded from memory, then we add 1 to, well, it's technically called a register, so I'll just use that term. So the register where I is stored, and then we can store I back to memory. So while the Scala allows us to write this as one simple statement here, really there's more going on. And this is what gets us into problems. It's possible that one thread loads the value of I, and then before that thread gets to the store, another thread loads the same value of I. In fact, on the machine I'm running on, it's quite possible that another thread loads the same I and another thread loads the same I. So multiple threads can get the same value of I. They all add 1, so they all get to the same value, and they all store them back. But that means that so if this loaded in 10, well, then I have 4 threads that increment it to 11. But those 4 threads should have wound up going to 14 because each one was trying to do one more increment. So they're all kind of competing with each other. We call this a race condition. As a general rule, if you have mutable memory, so vars, or if you're using arrays, or basically anything that you can mutate, so buffers as well, and you have 2 threads that are accessing it, and at least one of them is writing, you have the potential for a race condition. And because you don't know the order in which threads are going to execute, race conditions make your code completely unpredictable. This is one of the reasons we've alluded many times to the fact that mutability might seem like it simplifies things, but it can cause you problems. When you go to parallel programming, mutability makes things challenging. Okay? And so a lot of what we're going to talk about is how we can get around that problem, how we can do things either by avoiding mutability or by containing the mutability and making it so that we don't have race conditions. So there's a brief introduction to the parallel collections and an introduction to some of the challenges that come from making things parallel.